right. That effectively concludes that little quiz concludes our heat transport discussion. Oops. All right. So today we're going to start with mass transport and basically our final stretch for the semester. So we have basically a little 1 plus more than 2 weeks left because the semester ends on Monday, December 10th. That's a little different than usual, so just have that in mind. So the chapters that are relevant to mass transport are that we're going to cover are 17, 18, and 19. This introduction is talking about chapters 17 and 18. The structure of what we're going to go through is similar to what we had before, and that's the whole point of teaching all these types of transport together. You have possibly on your undergrad taken fluid mechanics separately, and then heat transport separately, and mass transport separately, possibly heat and mass together, and fluid mechanics separately, or some sort of combination like that. The whole point of this course is to actually put them all three types together and discuss them in one course. So we will start this with a very short discussion on molecular basis that is very similar to what we've done at the very beginning for momentum transport coefficients. So we are not going to spend too much time, but just to get stress that everything starts from the molecular basis, even if we can't always afford to simulate everything or to think about all of the molecular details. And then the key part of the problem solving is using shell balances. Equations of change are also shell balances in a nutshell. So we are, and then this is if time permits, and time never does. So we're we're not going to go into Taylor dispersion. Just in case you do end up doing it for your research, do check out chapter 20 for that. And then we will have a short discussion on time-dependent problems and dimensional analysis. Okay? And that is basically our plan until the end of the semester. So let's start with mass transport. So far, we've mostly looked in terms of momentum transport. We've looked at the transport of the entire phase. Okay? So we have some phase that we're following, and we are assuming it's homogeneous, at least as far as momentum transport is concerned. However, we always know that each phase, like even if you're looking at water, which is typically a brine phase because it has a lot of the dissolved ions in there, it's a combination of multiple chemical species. And all of them do have their amine on their own. Okay? So technically, diffusion refers to the movement of a single chemical species, okay, in response to the different concentrations in different parts of the medium. So even though I might actually have a brine as a phase, different ions could be diffusing within that brine and be transported on their own within that phase. So from the momentum transport perspective, I wouldn't even take that into account, right, as a bulk movement of any sort, but there is diffusion going on. So in a more simplistic way, if I had some fictitious membrane that is separating two types of molecules, okay, we know that molecules are moving around and they have their random velocities and they're bouncing around. So simply because of that, okay, molecules from this side will end up on this side, right? So in the moment I have more of these on this side, there's a more chance, probabilistically, that some of them will end up on the other side. There's simply more chance for more of them to do that than it is the other way around. Therefore, spontaneously, we're going to have movement from the higher concentration to the lower concentration. Nothing other than just things randomly moving around and ending up in another spot. Okay? So that kind of happens passively. There is no, other than this concentration gradient, there is no energy that I need to throw into the system for this to happen. It's simply going to happen. The moment I have different number or different concentration of particles of certain kind in one side versus the other side of the medium. And somewhat separately, the same will happen for the other type of species. They will actually diffuse in the other direction. So even though if I look at this container, the phase on its own is deemed stationary, okay? I can spray something on this side of the room. I technically deem there's no airflow unless the air conditioning is working and moving things around. There's no airflow in this room, but the particles would actually interdiffuse from higher concentration to the lower concentration. So this is, of course, difficult to track down, okay? So if I'm actually modeling. And in any realistic modeling, we know that we have multiple species. We're typically going to look at one that is of interest. We're going to label that one A, and then everything else will be B. so my mixtures will always be binary, magically, okay? Even though I do have much more than two species, I will typically look at one thing that I'm interested in that has high concentration gradient, that is moving to equalize that gradient, and it's moving in between everything else that I'm actually not really tracking down. Now, if I might have a reaction or something of that sort that might have more than two species in there, of course I'm going to track all of them, but technically for the most time we're going to have A, which is what I'm tracking down, and B, which is everything else. Okay? So some everyday example is, of course, so I just actually did like if I spray something on this side of the room, it's going to equilibrate. If I have just like sugar in your, if you use sugar in your coffee, I do actually honey. So basically, you will have a higher concentration, and you're going to start equilibrating that concentration. Now, the problem with a cup or coffee or anything like that is that there is also gravity. Okay? So even though the sugar that would actually fall down on the bottom of the cup would attempt to interdiffuse and equilibrate the concentration, it might have a hard time working against gravity. Okay? In which case, I actually have to help it and stir. Okay? So there are certain things that are not going to happen unless there is a different dominant transport or physical process going on. Okay? I could also have the same thing that we're doing is when we are opening a can of soda or a bottle that is under pressure and has a lot of CO2 inside, then basically we are creating a gradient the moment we are opening that, right? So basically at this interface, we're going to start drawing CO2. So the same, you can watch that in a bottle of any drink that has been carbonated. When you open, you're going to actually bubbles will start getting drawn to the surface because you have introduced a concentration gradient. Okay? So those are certain examples that we have in everyday life. Now, just to disambiguate, we will call diffusion also dispersion. In terms of mass transport, those things are the same. So when we look at the diffusion, we are thinking just about this. I have different concentration gradient, and that's what's driving my transport. Okay? Now, I could have in wave phenomena, dispersion could be something completely different, and that's not what we're looking at here. So you might actually have separation of waves in different frequencies while passing through a material or through an interface between two different materials. That's not what we're talking about here. So when talking with mass transport, dispersion and diffusion will actually mean the same. Now, in porous media transport, when I'm looking at mass transport together with all the others, Diffusion is actually typically much slower than all the others. So if I have actually momentum transport happening, it's quite likely going to be the dominant kind of transport. But it does become competitive on small scales. Okay? So recently there's this entire shale boom that is happening in the United States. So shales, or more generally mud rocks, are rocks that have extremely tight spaces, pore spaces. And they're a combination of silt and clay in various amounts, and they could also be quite carbonaty too. A whole lot of things are called or referred to as shale. But when we think about shale, we typically think about low permeability rocks that have very small particles that comprise them. And that causes the pore spaces, of course, to be even smaller. And in those pore spaces, momentum transport can be actually extremely slow. Now, when I talk about small pore spaces, if you actually look within kerogen, within the organic material that is also mixed in with the silt and clay, or if it's not mixed in, you're not interested in it, okay? So organic material is of interest in shale. That organic material will have pores that are nanometer scale. So you need a very high resolution SEM to actually just even look at them. And you will find these sort of like bubble looking from gas expulsion inside of the kerogen. You have pore spaces that look like small bubbles within that material. And those bubbles are on the order of 10 nanometers or even less, 10 nanometers to 50 nanometers. There are measurements of pore spaces that are even below 2 nanometers. And those are actually within the kerogen itself that is separating those bubbles. You can find it's like a little sponge, so you can find very small pore spaces. They're not our pore spaces as we imagine them in between grains. However, in those pore spaces, if, say, I have 5 to 10 nanometer channels or bubbles, or basically distances between the walls are 5 to 10 nanometers, what is the size of a methane molecule? Roughly. It's angstrom, right? So it's like 3-ish angstroms, that all these smaller molecules. Larger size molecular chains are larger, but they also have a different way to move through. So let's just look at the more compact molecules, such as methane or water. They're 10 times smaller, 10 to 20 times smaller than that channel. Therefore, I cannot think about, even if it's filled with methane, that pore, I cannot really think about the continuum phase the way I think about it normally. My continuum phase assumes that I cannot see all of the details in the individual molecules. It's acting as some bulk phase. If I have a channel that is only about 10 to 20 times larger than the molecule itself, that molecule will see more collisions with the walls than it will see with its own phase, in terms of just molecular collisions. Therefore, it's going to start behaving differently from what it would be if I actually had a larger space, a larger channel, and bulk space. So that's actually right now area of active research. Measurements are of course insanely difficult. So some of you are working in micro models, right? So you create micron-sized channels by etching. Now think about controlling and creating a micro model that has nanometer size. Just like verifying how does it look like, right? Are things bonding? How clean does your clean room have to be so that you don't mess up something on that small of a scale? So there's extreme difficulties creating models for such type of spaces, observing them in nature. And then ultimately I'm interested in how things behave on the field scale. So now I'm upscaling even from smaller scale than we used to before. So a lot of things that we normally think about in porous media that come really from sandstones and granular media that are well studied do not necessarily apply on that small scale. So all of the interpretation that I have if I go through bell logs and formation evaluation, most of those relationships have been created from models of granular materials that have particles that are on the 100 microns and above. And they work well for those, which are typically conventional sandstones and granular materials. However, the moment I have this very small pore spaces, it's extremely hard to interpret. So models that we have are lacking and are right now intense area of research. And also just if you think about larger molecules, if you have more complex hydrocarbons, how the more complex molecules and larger whatever polymers we might inject into the porous medium, how are those molecules start going to move and filter through these very tight pore spaces is a very good question as well. So one can actually see that in the research areas, there's like a lot of molecular dynamics simulations that are entering petroleum engineering that have not traditionally been used in petroleum engineering because they were deemed too small. Okay. All right. So here's our notation for these binary mixtures. So as I mentioned, we're going to have typically a species that I'm tracking, which is species A, and everybody else, which is B, or maybe I'm just looking at two species. So I'm going to refer to now, normally when I define density of a bulk phase, this brine that I was talking, it was just density of entire brine, rho, divided by V. Now I'm thinking of this rho as a sum of two species. So my density, rho, is rho A plus rho B. So when I look at the mass concentration or density of individual species, it's going to be mass of all of the molecules that belong to that species A, Ma, divided by volume. Okay. So basically, my rho A is still going to be the same units as the regular density, but it's going to refer only to that one phase. Okay. Mass fraction is going to be rho A divided by bulk. So rho A divided by rho. And a lot of times we're actually going to work with fractions when computing these things. And these fractions are between 0 and 1, of course. So they're normalized. And all of the fractions, of course, are always summing to 1. So if I have just 2, they're summing to 1. But I might have more n of them in general. They're summing to 1 as well. We can also look at the molar concentration. So basically, this is number of moles of A. I have a correction here. Divided by volume. And that I refer to Ca. And again, for the entire system, C, molar concentration of the entire system, is the sum of the individual molar concentrations. And by the same token, I'm going to look at the molar fractions as well. So I'm going to take Ca and divide by the molar concentration of the entire system. And that will give me a number between 0 and 1. Sum of all of such numbers is 1. Okay. So it's quite an alphabet soup, and that can be a little difficult to track down. That's one thing that is kind of specifically different for mass transport compared to the others. You have all of these things that you're listing for each individual species. All right. So I will also now look at the velocity of individual species. Okay? So when I look at VA, there's a velocity of species A. So it's basically average of all of the molecules of A that I might have in the system. Okay? And when I look at the velocity of the entire system, I can average it by mass, or I can average it using molar fractions. So those are two different. They're not necessarily always the same. So my mass average velocity is these fractions that are between 0 and 1, omega A VA plus omega B VB. So my momentum, rho V, of the entire phase is also sum of individual momenta, rho A VA plus rho B VB. Now, mole average velocity is the same thing. We're going to denote it with star. So I'm going to do the same thing for mole average velocity, but I'm going to use molar fractions instead of mass fractions. So I have XAVA plus XBVB. And then I have this equivalent of the momentum, which is molar density of the system times mole average velocity is CAVA plus CBVB. Okay, so now let's do an equivalent law. We're used to these simplistic laws that are always relating flux of whatever it is that is moving in a linear way to the gradient that is driving the entire thing. So now I'm going to look at the diffusion, and I'm going to look in the most simplistic case without any bulk movement of the phase. So I'm just going to take a slab of silica, which is solid, so there's no fluid movement, and expose it to helium, which is what I'm referring to as my species A here. Okay? So on one end, I have a whole lot of helium and high concentration. On the other end, I have 0. Okay? And helium will diffuse into the silica, and there is certain maximum of it that it can actually diffuse. So right outside of it, I have 100% helium. But right at the border, I have some maximum concentration that silica can take. Okay? And I'm referring to that as omega A0. So after some time, I'm going to start having helium diffusing through. And after some time, I expect a linear concentration profile that develops. How do I get to that time is actually what we will refer to as time-dependent problems, and that's coming up next, by the way. Okay? So how I reach that steady-state profile. So at steady state, for this to continue, I have to have a continuous supply of helium on the bottom that is keeping this concentration omega A0 the same. And my flux, which I now refer to as J, flux of helium, JA, in y direction, is the mass flux W of helium divided by the area. So area is my plate area S, and I am now referring it to it as S because I'm using A for something else. It used to be A so far, this area S. Right? So basically, I know that same thing as before. I should be proportional to the actual difference in the concentrations, inversely proportional to the distance that I have to travel. And then I have a coefficient of proportionality here, and I'm going to break it up. I'm going to refer to it as rho times DAB, where rho is my density of my entire system. And DAB is this coefficient diffusivity that is going to be important for mass transport. And when I say AB, it's diffusion of A with B present, right? And of course, these DAB, the A can be different depending on what B is, right? So am I diffusing in silica? Am I diffusing in water? Am I diffusing in something else? So we do have to differentiate who is diffusing and where are they doing it. Okay. So in 3 dimensions, I would of course look at all of the directions, not just y direction. So I would have the same rho DAB times gradient of my concentration. This is assuming that diffusion in all of the different directions is happening in the same way. Back to our shale, shell, if it has a high clay content, okay, then it might have a high, like lots of platelet part, well, depending what clay is, but sometimes when it's like platelets, okay, they're going to be arranged in a specific direction, and I'm not going to necessarily have the same behavior in all of the directions. So there might be directionality to it, so I might have diffusion or any transport of anything different in different directions, okay? Which might come from the structure of the porous medium when we have porous media. Okay. Okay. So this is very similar to our heat transport, right? And it's simpler than momentum transport in the sense that I'm not looking at the gradient of a velocity field, I'm looking at the gradient of a scalar field, which is concentration field. Okay, so what are the units of this DAB based on these? Can you figure out the units? Take a piece of paper.
Is mass per unit area per time.
I'm going to have here mass per volume that I'm kind of scaling out. So what is left for D? It's very similar to some other normalized coefficients. Meter square per second, yes. So it's very similar to kinematic viscosity, right? So I can compare it to. So just like before, when we are comparing different types of transport, there's a Prandtl number, which is now different Prandtl number. So we had momentum versus energy transport. Well, I could also have momentum versus mass transport, right? So analog of Prandtl number will be Schmidt number. And it's going to look at the momentum. This is kinematic viscosity divided by DAB. So again, kinematic viscosity, DAB, alpha, which is normalized thermal conductivity, they all have meters square per second. And then if I multiply it, if I do have also movement of the fluid, I can multiply that number with Reynolds number, similarly like we did for heat. And that number, both are called Peclet number. So there's Peclet number for heat transport and Peclet number for mass transport. And that is the most commonly what's looked at, because most of the time you're going to look at the combination of momentum or the fluid movement and mass transport and its interrelationship. We will rarely look at all three together, even when we have to, because it becomes really complex. And then you could also compare heat versus mass transport, and that gives me Lewis number. All of these are dimensionless numbers. Okay. So when I'm talking about flux, J, so JAY and JBY, so I have this two species. I have A and everything else that I call B, okay? Or I can just assume I have two species. They're defined with respect to the center of mass. Okay? So technically, by definition, JA is my rho A times the velocity of my phase minus the mass average. So this is what I mean that they're defined with respect to the center of mass of the entire system. So this flux refers to the relative movement of the phase, and it's basically only because of the concentration gradient. Okay. Now I could actually reverse everything and talk about JBY, right? So if I have multiple species, and if I have two systems, just two species, you could actually look at the dBA in terms of a transport coefficient is the same as the AB. And there's a little example that you can work on if you'd like. So dAB is the same as dBA if I have two different things. And this is in part because we are defining this transport with respect to the center of mass of the entire system. Okay, so let's just look at some example values. So here I have some values that I pulled out just in centimeters square. They're in centimeters square per second. I have pulled them out from chapter 17. So let's look at our helium in silica. Okay. That's this last one. This transport is very slow, diffusion. Okay. So the transport coefficient is on the order of 10 to the minus 10 centimeters squared. Okay. Now if I had two liquids, or if I had ethanol in water, then that would be faster, right? 5 orders of magnitude. And then if I had gases, gas in another gas, such as CO2 and nitrogen, then it's the fastest. And that's something that I would expect simply because of the mobility of these molecules in their state. Okay. All of these are assumed for relatively low concentrations of A. Okay. In general, this diffusivity, it does increase with temperature. So at these lower concentrations, I'm assuming that my diffusivity does not depend on the concentration itself. At higher concentrations, it might. Essentially, if I have molecules of A diffusing through B, when I'm looking at the diffusion, I'm assuming that A is mostly bumping into B along the way. Okay? The intermolecular collisions, I'm mostly colliding with B's. If I have a higher concentration of A, then I'm colliding with both, and the analysis becomes more complex. So in that sense, we are assuming independence of concentration, because if I start looking at the higher concentrations, that becomes difficult to look at. And of course, in liquids and solids, it's much more dependent on concentration, because essential diffusion is much harder through liquids and solids, again, because of also or strong intermolecular forces. Okay, so in this case, just like in all of the others, we have the same message that we keep repeating. So flux happens when there is a gradient of potential. And ultimately, these mechanisms of momentum, heat, and mass transfer are molecular. So technically, we should be able to compute our diffusivity based on the molecular motion. So we're going to do just a brief overview, but there's the same kinetic theory that applies. So let's, just for this basic understanding of how diffusivity constant is coming to be, let's look at the kinetic theory approach. Okay. So this is a familiar picture that we had before. So I have my gases at low density. Okay. I'm assuming they're little tennis balls that during collision they don't lose any energy. And I impose a concentration gradient. So before it was temperature gradient, and before that it was velocity gradient. So now I'm just like in that slab of silica. I have, it's just not now a slab of silica, but it's just gas on its own. I have the concentration gradient, and I have much higher concentration on the bottom. Okay. Now, from kinetic theory, we know what is what is the mean free path between two different collisions, and what is the average distance in planar distance between those collisions. So they're given by the formulas that we've seen before. I know what is the average speed, and velocity directions overall are randomly oriented. And I know what is the frequency of molecular bombardment on one side of the surface exposed to gas. Now let's simply compute the flux. Just like before, okay, I impose this gradient, and then I'm looking at the flux of molecules, which ultimately is all the molecules that are going in upwards direction, in y direction, minus those that are going down. Okay. And I need to count them up using these statistical formulas. Okay. So we're going to have here a simplifying assumptions that we're diffusing among the same type of molecules, so these formulas actually apply. Okay? Because these formulas are just for one type of molecules. So I'm going to refer to that as DAA, essentially, or A star. Okay? And I'm assuming this gradient that I assume it's linear over the couple of these lengths A. So I can use a very simple chopped down or simplified Taylor's formula that has only first derivative in there. Cool. So this is all that we know. And then when we actually look at the mass flux across a plane, okay, then I look at all of the molecules crossing in plus y direction minus all of the molecules crossing in minus y. Okay. So Z is the number of them, that is my molecular bombardment. Mass of the molecule, I'm just looking at the mass of single type of molecules, is MA. Okay. And I'm carrying information, so when I'm crossing in plus y information, direction, I'm carrying information from my last collision, okay, which has happened at this plane y minus a. And the same thing when I'm crossing down, I'm carrying information from my last collision, which has happened at y plus a. Okay. So this is my mass WA, mass flux. Now, I plug in what this formula for Z actually means. So it's 1/4 number density times U average speed times MA. Okay? And it's this number density that actually differs at these different locations. So average speed is assumed the same. So my number density, number per volume times mass of the molecule, each molecule, gives me actually my rho A. Right? Mass of all of the types molecules A divided by volume. And that by definition is rho, my entire phase rho, times omega A, which is fraction. This fraction is defined as rho A divided by rho. Yes? And since we impose this concentration, we impose the gradient in omega, so that we have to get down to omega. Oh, okay. Well, let me just quickly go over this. So basically, that is my rho omega A that differs at these different locations. So this is where I plug in my Taylor formula for omega A. Okay. And when I do that, whoa, hi, yes, I know. Like my calendar really wants me to know that I have a next meeting at 10 o'clock. And basically, I plug in omega A, Taylor's formula, and this is where I'm going to get the gradient. Okay. And once you plug all of that in, you get the mass flux on one end, you get gradient, and you get things that are depending here. There's rho times something that depends only on this type of molecules that I have without depending on the concentration itself. And that is what my DAA is. Okay? So it's a similar procedure as we had before. One tricky part would be recognizing this. Okay, I see you on Wednesday.